Hello, everyone. My name is Charlie. I'm a research scientist with the Tensor Learning team at IJCAI'25. In this section, I will be talking about tensor algebra with a particular focus on tensor networks. By the end of this section, you will understand what a tensor is, how to construct tensor networks, and how tensor algebra can be used to improve both the computational efficiency and the parameter efficiency in machine learning, and even beyond. I've organized my section into three parts. First, I will introduce the basics of tensor algebra, covering tensors, tensor contraction, tensor networks, and so on. Next, I will talk with you through the recipe for using tensor networks in learning models. Finally, I will discuss practical applications of tensor algebra, highlighting our recent papers that apply the tensor networks in the real-world problems. So, let's start with the basic question. What is a tensor? You can think of a tensor as a multidimensional array of real numbers. Here in the figure, we have three dimensions, I, j, and k. Each little cube represents a single number, and together, these numbers form a simple example of a tensor. What's interesting is that many types of data we work with every day naturally have this tensor structure. For example, a video is basically a sequence of images, so you can think of it as a tensor with height, width, and the frame directions. In brain MRI, we often have three spatial dimensions, and sometimes even a time dimension if it's a functional MRI. For the multispectral images, we capture not just the spatial information, but also multiple channels across different wavelengths. So that is another dimension to the data. All of these examples can be naturally viewed as tensors. The key point here is, tensors are not just an abstract mathematical concept. They are a very natural way to represent complex, structured problems, not just for data, but also for learning models you will see later. This is why tensor algebra becomes so powerful in scientific computing and AI. Now we have known what a tensor is. Next, let's connect it to some concepts you already know in linear algebra. A scalar is just a single number. So in the framework of tensor algebra, we call this a tensor of order 0 because it has no directions. A vector is a one-dimensional array of numbers, so this is a tensor of order 1. A matrix is a two-dimensional array of numbers, so it's a tensor of order 2. It has two directions corresponding to the rows and columns. So we can see the tensor's order just means the number of directions. And we call these directions to be the tensor modes. And we call the dimension along each direction mode dimension. Another way to understand tensors is to see them as stacks of vectors or matrices. Let's start from the top row. A horizontal slice is what you get when you fix the first mode I and keep the other two modes free. That gives you a 2D matrix. A lateral slice is when you fix the second mode J. Similarly, a frontal slice is when what you fix the third mode K. So you can see each of these slices is just a matrix taken from a different direction. On the bottom row, we have fibers, which are like the one-dimensional strands through the tensor. So, a mode 1 fiber is a column vectors obtained by fixing wall by the first mode. A mode 2 fiber is a row vector obtained by fixed wall by the second mode. A mode 3 fiber, sometimes called a tube, is obtained by fixed wall by the third mode. So, think of tensors as stacks of slices or fibers is very useful because many tensor operations are performed slice by slice or fiber by fiber. Now, let's look at a concrete example to understand a simple but important tensor operation called unfolding. First, let's recall what we've learned so far. Here we have a tensor A of order 3. That means it's an array of numbers with 3 directions, or modes. At the top, you can see A has 2 frontal slices, one in green and one in orange. Each slice is just a regular matrix, taken from the tensor along one mode. In the bottom part of the figure, we show unfolding, which is the process of mapping a higher order tensor into a matrix. Since the tensor A has 3 modes, we can unfold it in 3 different directions. In the mode 1 unfolding A1, we take all the mode 1 fibers that correspond to the column vectors of the tensor and arrange them as the columns of the matrix. In mode 2 unfolding A2, we use the same idea, but now it's the mode 2 fibers, corresponding to the row vectors of the tensor. In mode 3 unfolding A3, here we use the mode 3 fibers, also called tubes. It is important to note that each unfolding operation is linear and invertible. There are 2 key points I'd like to highlight here. The first point is, from the unfolding we can see a higher order tensor commonly contains richer structural information than matrix, because it can be unfolded into multiple matrices with the same group of entries. The second point is we can see once we have the tensor in the matrix form, we can apply all the linear algebra tools we already know, like the single value decompositions, multiplications, factorization, and so on. But we can apply these on tensors mode by mode. So, unfolding acts as a bridge between the tensor algebra and the linear algebra. In this page, we are going to learn about tensor contraction. Basically, it's how we define the kind of multiplication between 2 tensors. To get there, let's start with something we all know, matrix multiplication, and see how it naturally extends to the more general concept of tensor contraction. Suppose we have 2 matrices, G and A. Matrix multiplication works by taking the rows from G and the column from A, computing their inner product, and putting that result in the corresponding position in Y. For example, the second row of G and the second column of A multiply together to give us the value of 0.14 in Y. So in tensor contraction, it means if the G were a tensor of order 3 instead of matrix, you could picture it as a stack of the matrix slices. When we try to multiply G by A, we don't just work on one slice. We do the multiplication across all slices at once. Tensor contraction works like a matrix multiplication, but it's not limited to just the 2 modes. You can contract over any shared tensor modes you choose, which makes it much more flexible than the conventional matrix multiplication. Here's the example of what I mean. In A, we are doing a mode 1 contraction. You can think of it like a lift matrix product. We are multiplying along the first mode of the tensor, and the result keeps the other 2 modes untouched. In B, we switch to a mode 2 contraction. Now, it's like a right matrix product. We multiply along the second mode, and again, the other modes just pass through unchanged. And in C, we do a mode-3 contraction. Here we are multiplying along the frontal direction of the tensor. So the first two modes stays the same while the third mode changes. So we can see the key point here is the tensor contraction is multilinear. That means we can operate on each mode independently and linearly. And we can fix and match which mode we want to contract over, depending on the problem. This flexibility is what makes the tensor so efficient and flexible for representing and processing high-dimensional structures. Now, let's make this a bit more formal. Suppose we have two tensors, where A is a tensor of order capital N, and B is a tensor of order capital M. They are shared a common mode. The notation here means that A's N mode is shared with B's M mode. Then we can perform a contraction along the shared modes to produce a new tensor C. The result is a tensor whose order is the sum of the orders, M plus N, but minus 2, because the shared modes M and N is removed, is contracted in the process. So the notation here means that we are contracting the nth mode of A with the mth mode of B. If you look at the summation formula below, you will notice it's essentially the same logic as matrix multiplication. We multiply entries along the shared mode and sum them up like the inner product used in the matrix multiplication. Alright, let's take a quick break here and do a recap of what we've covered so far. We started with the definition of tensor. Basically, a tensor is a multidimensional array of real numbers. We looked at subtensors like fibers and slices. Then we talked about unfolding, which let us turn a tensor into a matrix, so we can use our familiar matrix tools. And finally, we introduced the tensor contraction, which is like matrix multiplication, but much more flexible in higher dimensions. Next, let's see tensor networks. So far, we've mostly been talking about the tensors of order 3 or less. But in many real-world applications, we have to deal with much higher order tensors, and that's where things start to get tricky. The challenge is that the number of entries grow exponentially with the tensor order. Even moving from a matrix to a tensor of order 3, you can already see the size exploding. That's why we need a smarter way to handle them. And that's where tensor networks come in. They give us a super efficient framework for representing and working with the very high order tensors. In the framework of tensor networks, we borrow the idea from the graph theory to model tensors and tensor contraction. Here's the trick. We use a node to represent a tensor and use the edge coming out of the node to indicate the mode. The labels on the edge tell you the mode dimension. For example, this node here with one edge label I, that's just a vector, a tensor of order 1. If it's got two edges, it's then a matrix, a tensor of order 2. And you can keep adding edges to represent higher and higher orders. Super simple. The cool thing about this notation is that it's all about how things connect, not about listing out a giant table of numbers. And that way of thinking, focus on connection, is exactly what's going to make tensor network work so well later on. Now that we know how to draw tensors as nodes, let's see how operations like contraction look in this notation. Take two tensors, A and B. If they share an edge with the same dimension, here is K, we can connect them. That connection means we are multiplying the tensors along the shared mode. In the first example, this is just a matrix multiplication. A times B gives us a new matrix X. In the second example, we start with a tensor X of order 3 and 3 vectors A, B, C. Connecting them means we are contracting along all these edges, and when we are done, we got a single scalar. These are two of the simplest forms of the tensor networks. From them, you can already see the basic idea of tensor networks. A tensor network is just a way to model complex tensor contractions across a whole group of tensors, all through their connectivity in the graph. With this graph-based representation, we can describe many different types of tensor networks suited to diverse practical problems. Next, I will zoom in on one of the most popular forms, the tensor train, along with its variant tensor ring, to show how tensor networks achieve the efficient representations in practice. The idea of tensor train is simple. Instead of storing a huge tensor of order n all at once, we break it down into a chain of smaller cotensors, each connected only to its neighbors. If we see how a single entry of the tensor is represented, we pick the relevant slice from each cotensor based on the index I1, I2, until In, and then multiply them all together along the shared dimensions. Because of the form of the multiple matrix multiplication, in physics, the tensor train is also called matrix product state. This is why tensor train is so efficient, because you replaced one huge object with a sequence of small, manageable pieces, while still being able to reconstruct the original tensor. Here's another popular format, the tensor ring decomposition. It's very similar to the tensor train we just saw, but with one key twist. Instead of forming a chain, we connect the two ends together to form a closed loop, like a ring. The reconstruction process is also similar. We take the right slice from each core tensor, according to the indexes I1, I2, until In, and multiply them all together along the shared dimensions. But because it's a ring, we also have to connect the last core tensor back to the first by taking the trace over that multiplication. The advantage of tensor ring is that it's symmetric under rotation. Every cotensor plays the same role, and you don't have the boundary effect like tensor train. This symmetry can give you more flexibility and sometimes better expressive power. We have shown when we represent a higher order tensor directly, the storage cost grows exponentially with the order. That's the curse of dimensionality. But if we represent it as a tensor network, like a tensor ring, the storage cost drops dramatically. Instead of storing I to the power of n entries, we only need about n times I times r squared, where r is the shared dimensions. We can see this is a huge saving in storage, especially when n is large. That's one of the key reasons the tensor networks are so powerful. Beyond storage, Tensor networks are also efficient when it comes to computation. For example, here we have two high-order tensors A and B, which can be efficiently represented with a tensor ring, and then we'd like to compute their inner product. Unlike multiplying them directly, which leads to the computational complexity of the I to the power of n, we can calculate their inner product by connecting the two tensor networks and contract them locally, step by step. This changes the cost from the exponential to something much more manageable, which is a massive speed up for large problems. At the end of this part, let's take a quick pause and recap what we've seen so far. First, we know the tensor networks are essentially graph representations of tensor contraction, nodes for tensors, edges for the shared modes. Second, the tensor networks gives us a powerful way to beat the curse of dimensionality by breaking down the massive high-order tensors into smaller and manageable pieces. And third, tensor networks are not just compact in storage. They can enable efficient computation, turning problems that were once intractable into something we can actually solve. In the next part, let's see how to use tensor networks effectively in machine learning models. The central motivation of using tensor networks is for the efficiency. In AI, efficiency isn't optional anymore. It becomes a must. From foundation models to quantum circuits, embedded intelligence, and to AI for science, we always face the high-dimensional operators that are computationally expensive. But once we can see them as tensors, the tensor networks give us a really powerful way to store them and do the computation much more efficiently. To have the efficient computation, the first step we need to do is tensorization. Since we can consider these operators as high-dimensional matrices, that means we reshape this big matrix into a high-order tensor. What we do is, we split the row and the column indexes of the matrix into multiple smaller tensor modes, turning it into a higher-order tensor. Once we have that, we can represent it using different tensor network models, depending on the problem's needs. As a result, the original high-dimensional matrix would be represented with much fewer number of parameters. Let's see how exactly this works, starting from just one neuron. In a standard neural network, a neuron's output is computed as this formula, where W is the weight vector and H is the input vector. If W and H are high-dimensional, storing and computing with them directly can be expensive. So, to achieve more efficient computation with tensor networks, our first step is tensorization. We start by reshaping the weight vector W into a tensor of order D by splitting a single long index into D smaller tensor modes, each of dimension m. We can do the same for the input H. Next, we represent this higher order tensor using tensor networks such as TensorTree, for example. Instead of storing the entire tensor, we store a sequence of smaller cotensors from G1 to GD. This significantly reduces the number of parameters from the capital M to roughly this value. Finally, the inner product of W and H becomes a tensor network contraction between the tensortron representation of W and the tensorized H. This computation can be efficiently done tensor by tensor. Now, Let's extend this idea from a single neuron to multiple neurons, as in a whole hidden layer. In a standard layer, we have a weight matrix W of dimension m times n, mapping the previous layer's output H1 to the next layer's output H2. The computation is shown as in the formula. So similarly, our first step is to use tensorization. We reshape W into a tensor by splitting both its row and column indexes into D tensor modes, and then H1 is reshaped into a tensor of order D. In the step 2, we represent the tensorized W as a tensor network, like tensor train. In step 3, the matrix vector product W transpose H1 now becomes a tensor network contraction. This contraction outputs a tensor of order D, which we can then reshape back into the next layer's neural outputs. So, just as in the single neuron case, we achieve massive parameter saving and computational efficiency. Now that we've replaced the full-weight matrix W with its tensor network representation of cotensors, then the loss function changes from the minimization of W to the minimization of the core tensors from G1 to GD. When we compute the gradients with respect to the core tensor, we apply the chain rule. It's from the loss function L to the layer output H2, and then from H2 to the pre-activation output O2, and finally from O2 down to the specific core tensor GK. The diagrams below illustrate how gradient computation can be also expressed as tensor network contractions, just like the forward pass. This way, the backward pass inherits the same efficiency benefits as the forward pass. So we can see, by working directly in the tensor network space, we reduced both storage and computation for both training and inference. In the last part, let's see how to use tensor networks to solve the real-world applications. The first example is parameter-efficient fine-tuning. This is a hot topic in adapting large models without retraining everything from scratch. Here, we start with a pre-trained weight matrix W. Instead of updating all parameters of W, we know the well-known LoRa fine-tuning inserts a low-rank adapter A times B. This means we only training a small number of parameters proportional to the rank R, making it much easier. Now, where tensor networks come in is that we can represent these adapters not as dense low-rank matrices, but as tensor networks. This is what the quantum method does. In the method, it uses the tensor networks to parameterize the adaptation space. As a result, this allows richer expressibility than the vanilla low-rank matrices, without the bottleneck of low-rankness in LoRa. In the figure, the graph shows that Quanta achieved better performance parameter trade-offs compared to LoRa, getting closer to full fine-tune while keeping the efficiency benefits. Now, let's see how we can fine-tune a diffuser model for medical imaging using a similar idea. In this case, we start with a 3D DDPM that pre-trained on the UK Biobank MRI dataset, and then fine-tune it on much smaller datasets of disease-specific MRIs. The challenge here is that the three-dimensional convolutions create huge and high-dimensional kernels, and the medical datasets are usually tiny, so the overfitting becomes a big problem. Just like in Quanta, we use tensor networks to represent only the parameters we fine-tune. This way, we adapt the model to the new data with far fewer parameters and reduce the problem of overfitting. Let's look in more detail at the key difference between the classical LoRa and the tensor network-based method. Both LoRa 2D and LoRa 3D use a simple low-rank matrix decomposition. It is efficient, but it suffers from the so-called low-rank bottleneck. But Tensor Network takes a different route. We keep the high-rank modeling and representing the weights using richer tensor network structures. This lets us capture the multimode correlations that LoRa simply can't, while still keeping the number of parameters low. Here, we are comparing generated MRI images from different fine-tuning methods across 3 disease-related datasets. You can see that many existing methods either lose the fine structural details or introduce variable artifacts. The tensor network-based methods, on the other hand, consistently preserve the structure and maintain the high image quality, even when we just use the parameter-efficient fine-tuning. This really shows that keeping the tensor structure during the fine-tuning not only cuts down the number of parameters, but also helps retain those critical high-fidelity medical features. Now, let's move to another application, that is the discrete probabilistic modeling. In this application, we are modeling probability distributions over discrete random variables. We have known for a solo random variable, the distribution can be seen as a vector, while for the two-dimensional random variables, we can then use matrix. And for higher dimensions, they naturally form high-order tensors. So the challenge here is clear. As the dimension of the random variables grows, these tensors explode in size. We thus need efficient ways to store, compute, and learn from them. This is exactly where tensor networks come in. In this page, we quickly go through 3 main ways people use tensor networks to model distributions. The first way is to use tensor network directly. It represents the distribution T directly using a tensor network, such as a tensor train. But here, we keep each core tensors non-negative and normalized to make the tensor T a legal distribution. The second way is called Born machine. It starts with a tensor network like a train, and then make a copy where each core tensor is replaced by its complex conjugate. Multiplying the two tensor networks guarantees a non-negative distribution, even if the core tensors themselves take any values. The second way is called LPS, similar to the Born machine, but it imposes additional construction between the core tensors to capture richer correlations. A natural question is, where do we encounter such extremely high-dimensional distributions in practice? Well, here's a clear example: prompt learning for text-to-image models. In this task, the model takes your text prompt, maps it into a sequence of tokens, and those tokens then guide the image generation process. Now, with the right prompts, you can do all sorts of things, from precisely controlling what the model draws, to even jailbreaking it and bypassing safety filters. But the task is challenging. The prompt lives in a huge search space. Its dimension grows exponentially with the number of tokens. To this end, we treat our belief about what the optimal prompt might be as a tensor network. Each mode in the tensor represents the uncertainty for one token in the prompt. Then, during the search, we sample prompts from the distribution tensor T. For each one we sample, we run it through the model, check how well it works using a task-specific loss, and record the evaluation result as good or bad. That evaluation result is then used to update our probability model, the tensor network itself. By iterating this process, sampling, evaluating, and updating, we gradually narrow down on the optimal prompt while exploring the space efficiently. Here, we first show the results for prompt discovery with the target image. The task here, given an image, we want to find the optimal prompt such that when we feed this prompt into a generative model, it can recreate the target image as closely as possible. At the top, you see comparisons. Our method consistently produces prompts that generate images much closer in style and content to the original compared to other methods. The table below shows the results across 6 benchmarks. For different lengths of prompt, our approach achieved the best scores in nearly every case. Next, we use the same method for jailbreaking the Stable Diffusion model. The goal is to find prompts that can produce restricted content, even the model has been purified with machine learning. The process is the same. We search for the prompts with the introduced sampling method to align with those dangerous words but jailbreak out of the filter. In the top row, you can see the result comparison. The original prompts get blocked by the filter, but with our method, we found alternative prompts that bypass the filter while keeping the intended meaning. The table below compares our method with the past works across 3 different settings. Across every metric you can see, our method beats the previous state-of-the-art. For example, on the Stable Diffusion V2 in the black box setting, we hit a 78.5% success score for jailbreaking average. This is a big jump over the next best method. The key point here is, modeling prompt uncertainty with tensor networks isn't just good for generative tasks like the prompt discovery. It is also a powerful tool for prompting generative models in the safety-critical evaluation. In the last application, let's take a look at how tensor networks are being used in data science and beyond. Here, the problem is that we often face incomplete and high-dimensional datasets. Think of them as large tensors with many missing entries. The challenge is to recover the full data efficiently without overfitting or blowing up the computation. Tensor networks provide a compact factorization that can model the underlying correlations in the data, allowing us to fill in the missing entries and reconstruct the complete tensor, while keeping the memory and the computational cost manageable. Here's the basic recipe for tensor completion using tensor networks. We start with our incomplete tensor with lots of missing values, shown here with the question marks. Then, instead of directly trying to fill in the missing values, we represent the tensor in a tensor network form. These smaller cotensors are connected by tensor contraction. Here we use the tensor ring. The cotensors would be optimized to approximate those observed entries. Once the tensor network is learned, we can reconstruct the full tensor, effectively filling in the missing values in a way that is both efficient and accurate. In practical application of tensor completion, we also need to use tensorization. That is to reshape the original data into a high-order tensor, especially for the completion task for natural images. But unlike the trivial reshaping operation, here we split the modes across different spatial information and channels. By this way, each mode actually corresponds to a different resolution or patch in the original image. For the loss function, we model the recovered tensor to be X, and then force it to have a tensor ring format. Finally, we restricted the X to matching the ground truth T on those observed entries. On the top of that, we add nuclear norm regularization to the core tensors, which encourages the low-rank structure of the model. This helps the model discover compact latent factors that can be accurately predict the missing value. In this page, we show the recovery results given in the original paper in 2019. We tried the recovery of the incomplete remote sensing image and tried to push the limits. That means we assume 90% of the pixels are missing. We can see from the result that even with such an extremely missing value, the tensor network-based algorithm can still recover the data with high quality. And more importantly, we can see this kind of method did image recovery without requiring any training data. Interestingly, this tensor ring completion method we proposed back in 2019 has recently found a surprising new application in physics. The method was used for the optimization in the process of the so-called renormalization group. And the renormalization group is an important tool to study the critical two-dimensional EC model. We can use it to analyze why the system shows the power law correlation. This is a signature of emergent behavior. These insights are not only important to understand the phase transition in physics, but also connects to the challenge of uncovering the emergent behaviors in foundation AI models. Just as in our earlier work, the method also involves finding the optimal tensor ring representation with the regularization applied to the lower order cotensors. Then let's see the numerical results. The left panel shows the single value spectra from an old algorithm. We can notice the irregular drop-offs and the instability as the renormalization proceeds. But on the right, it is using our method. The spectra are much cleaner and more stable, meaning the optimization avoids overfitting to short-term noise and preserves the physically meaningful correlation. The bottom compares the error in free energy between methods. Our methods consistently achieve the lower error at the critical point, showing that this method really helps stabilize the simulation of the phase transition. This page is the end of my section. Thank you so much for listening. In this tutorial, I hope you've gained a clear picture of what tensor and tensor networks are. Learn the basic recipe for applying them in learning models and think how they can tackle real-world problems. If there's one thing I want you to take away, that is, tensor networks are more than a mathematical tool. They are a bridge. They started in science, grew up to power AI, and now AI is sending them back to science. From fine-tuning and prompt learning to modern critical system in physics, the same core idea keeps finding new and surprising homes. It is a loop from science to AI for science. In the middle, it is tensor network. And with every turn of the loop, we open a new door to the next wave of discovery.